Okay. So our final speaker of the conference is Hülya Argüz, who is coming to us from France. And she is going to tell us about mirror symmetry for log Calabi-Yau pairs.
Thank you very much for the invitation. Great pleasure to be here and to give a talk here in the 3CNG workshop. So what I'd like to tell you today is about mirror symmetry for log Calabi-Yau pairs xt given by a smooth projective variety x and anti-canonical simple normal crossing divisor d. And I will tell you about A1-curves and canonical wall structures and how they play a role in understanding mirror symmetry for such pairs. Then at the end of the talk, I will tell you of explicit equations for mirrors to log Calabi-Yau pairs. And the main result I'd like to communicate today is that there's a purely algebraic algorithms to compute all A1-curves in such pairs, as well as to obtain explicit equations for mirrors for them. So just to give a one-page motivation, my motivation on mirror symmetry comes from the Strominger-Yau-Zastrow picture, which roughly says that in some appropriate limits, and some large complex structure limit and large volume structure limit for the complex and symplectic structures, mirrors admit two special Lagrangian torus vibrations. The fact that everything works very well in nice limits suggests that we do really need to consider families. So the mirror to Calabi-Yau from that point of view really comes in a family. So if it would come as a single Calabi-Yau, if you would just look at C star obtained by removing from P1 the 2 points 0 and infinity, so it admits this torus vibration over the momentum polytope of P1, where the endpoints are removed. And if you would like to try to understand this YZ picture, there is, like, thanks to Yau's theorem, whenever you have a Kähler form, there is a Kähler metric. From this point of view, the dual metric would just trade the circle with radius r with a circle with radius 1 over r. And then you would have the dual vibration, again given by a C star. But what we want to do is we want to understand x and limits. So we want to build a family of such C stars which appear as such mirrors. And so I will tell you first how to construct this family of C stars in this basic example, and then tell you about more general examples. So the Gros-Seibert program is a program which aims at understanding, given a Calabi-Yau, how can we construct a mirror family to it? In the easy case, this Calabi-Yau, in the primitive case, could be imagined as a toric variety minus its toric boundary divisor. By toric boundary divisor, I mean the canonical there are too many canonicals in the literature. The anti-canonical divisor, which is naturally defined by just looking at the union of divisors which are fixed under the torus action, like the P1 example together with 0 infinity fits into such a case. So what is the mirror? If you look at the toric log Calabi-Yau pair, the mirror to the complement is a Calabi-Yau, but we generally just say the mirror to the pair. We need to fix this theta given by Rn together with the toric fan of this toric log Calabi-Yau pair. And then we fix the monoid Q, which we take as the monoid of integral points of the cone of effective curves. And then we fix a piecewise linear function, which is a linear function on each maximal cone of the toric fan. And we want this function to take values in this. It's a monoid valued function. And such a function is determined uniquely up to a linear function by specifying its kinks along codimension 1 cones. And there's a canonical choice to declare the kinks of such a function. For instance, if you look at this example P1 0 infinity, then H2 is N, it's generated by the class of a P1. And then I can define a piecewise linear function. In the fan I have just the codimension 1 strata, the origin. I naturally declare the kink of the piecewise linear function as the corresponding curve class, which is just a P1. So there's up to a linear function, a unique piecewise linear function, which has kink like this. You can either draw it 0 and with slope 1 here, or it could be 0 and with slope 1 here. So you can add and subtract linear functions. But we solve the matter by up to a linear function ambiguity. By imposing that, we always fix a point in some maximal cell in the fun, and we impose the piecewise linear function to vanish at that point or at the maximal cell containing that point to solve the ambiguity. So there's always a unique function like that when you impose that you want it to vanish at some chamber. And the mirror in this case, what is the mirror? So you just look at the upper Hall convex cell of the graph of the function, and then you declare this to be the momentum polytope of the mirror family. So if you have a toric variety whose momentum polytope is this, this family is just spec, this Morricone notation. So I just have one variable t to the curve plus p1 coming from this monoid. And then you have xy corresponding to raised xy and xy equal to this variable t to p1. So this is my mirror family. This is a family of C stars indeed, degenerating into a union of two copies of A1. So to sum up, I declare my monoid P, I define a monoid P by taking the PL function and the graph and everything above it, the monoid of integral points, and everything about the graph of the PL function. And the natural inclusion gives rise from Q to this P gives rise to a family, and this family I declare my mirror family. And we are calling this the ring of theta functions, this KP, which is the coordinate ring for the mirror. And why do we call this the theta functions? Because, so you see, this plays the role of the momentum polytope. So there is some duality. The idea of SIZ suggests that the momentum polytope is replaced by the fun when you want to construct a dual vibration. So you start with the fun, but you build a momentum polytope for the mirror out of it, and every integral point in the momentum polytope corresponds to some theta function, honestly. And these theta functions are defined by, so if you have an element in the monoid, if you take the corresponding element in the monoid ring, so you have these theta functions, which are of the form z to mi phi bar mi, where mi is so I'm just writing the generating theta functions. So for my ring of theta functions, I have generators given by theta functions, which only correspond to the rays of my toric fund. So here I have two ray generators. My mirror family will be generated by two theta functions. And I write those theta functions as theta mi p of this form z to the mi, my PL function valued at mi. And there is a dependence on the point p. I fix a point, general point on a maximal cell, and I impose my PL function to vanish on the maximal cell containing that point, and that way I ensure I get a unique PL function. Let's do this example with theta functions. If I look at a mirror of P1 with 2 points, if I write my theta functions using the definition, so theta1, I look at Z2 so it is z to 1, which is x. This element in the monoid ring I call x. Then the value of phi at 1, which is, it takes value p1, t to p1. And theta minus 1 is just x inverse. So I have theta1, theta minus 1 generating my mirror. Apologies, there's a mistake here. Minus 1, 0 should be just minus 1, and 1, 0 should just be 1. So my mirror is theta minus 1, theta 1, such that theta minus 1, theta 1 equal theta n. But what we do generally, we never really draw this picture of the momentum polytope of the mirror. We always work with broken lines in the fan on the base to tell you what the theta functions are. So there is a very nice combinatorial procedure to tell you what the theta functions are, defined this way. And that procedure is provided by, we use broken lines. So broken lines to define theta functions as follows. So a broken line is the image of a map from -∞ 0 to Rn, with some endpoint. So it's a line segment. It's composes of many line segments, but in the toric case, they actually, broken lines never bend. They will only bend in more interesting situations. So in the toric case, as in this picture, there is one blue broken line. It's just the image of a line segment which stops at some point P. And this P, I'm choosing the same point that I fix in the interior of some maximal cell that I choose while trying to get a uniquely defined PL function, which vanishes at P. So I look at broken lines which stop at P, and these broken lines carry some monomials. And the rule is each time you cross a codimension one cell, those monomials get the contribution of the kink of the PL function. So if you choose the point P here, if you look at the broken line coming from this direction, -1 direction, you declare your θ1 to be the monomial it initially carries. The direction it comes from, the broken line, it initially carries the monomial x inverse. So your θ-1 is just x inverse. If you want to understand θ1, you look at the broken line coming from the one direction, it initially carries x, but it does cross the origin to come to the point P. So θ1 is x times T2P1. So you see, you can write your θ functions very conveniently in a very combinatorial procedure by making use of broken lines and just by analyzing the fun picture of your toric variety. Before proceeding with more examples, I just want to do a final example. So if you, by NEX, I denote a moricon, which is the cone of effective curves associated to X. If I take X, again, a toric variety obtained by P2 blowing up a toric point, then the mirror is obtained as this. So you have P2, you blow up a toric point, which means you chop off from the momentum point of this part, which means you add a ray and a fun. I love drawing all the curve classes here. When what happens if you blow up, you have an exceptional class, a curve with class E. The curve classes, if L is a general line in P2, these are the curve classes after the blow up. So I like drawing them on the fan picture to remember what are the kinks of the PL function I'm choosing. And then I fix a point. Again, I take a PL function which will vanish at the cell containing the point. Then I write my θ functions. I have 4 unbounded directions corresponding to 4 rays. So my θ1, 0, if I come from 1, 0 direction will be x. If I come from 0, 1 direction will be 1. If I come from -1, 0 direction, it will be x inverse θl minus e. Because if I come from -1, 0 direction, I start my life at x inverse, but I do cross this ray which carries the kink L minus e. So it changes to this. And if I come from -1 direction, I start the life, the θ function, θ-1 starts its life with x inverse y inverse, but it does cross the codimension one cell, which carries the kink L of the PL function. So it turns to this θ function. So these 4 θ functions, so my mirror is generated by these 4 θ functions. Mirror family is given by this. You see there are obvious relations. This times this is equal T to L minus E, and this times this is T to L. So this is my mirror family. All right. So the main question is about more general XT. So we understand well by now how to construct mirror families for toric Calabi-Yau pairs. But how about if I take, for instance, the blow-up of a toric variety along general hypersurfaces, and if I don't assume these hypersurfaces are toric hypersurfaces, if I do non-toric blow-ups, so I will consider these situations, and in these situations, we do also know how to write explicit equations for mirrors running to gross seabed. Well, in dimension to gross cycling seabed, an arbitrary dimension gross seabed algorithm. In this situation, XT is called a local Calabi-Yau pair with a toric model. So I have my toric model X sigma D sigma, and I'm looking at a situation where I blow up along hypersurfaces in the toric boundary. And I wrote a paper providing explicit equations for mirrors in these cases, and I wrote several explicit equations explaining how the algorithm works. So these provide the first concrete equations for mirrors in higher dimensions. Apart from there was one case for studied by Tom Duca, there was one three-dimensional manifold where we understood their mirrors. So these provide the first non-trivial examples of higher dimensional mirrors where we understand the explicit equations. And to understand the explicit equations of mirrors, what we need to do is find an analog of the toric fun for non-toric varieties. So how it worked in toric situations, we endowed the toric fun with some additional data by PL functions, and we counted theta functions there. So if you have a non-toric blow-up, what will replace the toric fun for a toric variety is a scattering diagram or a wall structure. Depending on boundaries around or not, you call it however you like, it's the same thing. So I call it a wall structure because I'm still a former student nowadays of bound. So it's the canonical wall structure that replaces the toric fun. And this is a combinatorial gadget which encodes all tropical analogs of A1 curves. So what are these? These are images of stable rational maps in your local ABR pair, which touch T at a single point. And why do we look at such A1 curves? It's actually very natural. I mean, if you blow up a toric variety at a toric point, what you add is you just add the ray corresponding to the exceptional curve. So when you do non-toric blowups, you want to encode the data. You want to build a fun encoding the data of all exceptional curves and all curves that touch the boundary at one point, more generally. So we define the canonical wall structure associated to a local ABR pair as follows. You look at the tropicalization of XD. So there's a way to tropicalize a toric local ABR pair easily, which will just be the toric fun. In general, there's a way to tropicalize a local ABR pair. It only makes use of the intersection numbers of the components building your boundary D. And I will tell a bit more about this in a second on an example. And each codimension Lanza is endowed with a wall crossing function given by this formula. X of k tau is some multiplicity constant coming purely by computing some combinatorially by looking at lattice indices. This is a Gromov-Witten type invariant. This counts all A1 curves. This is the number of all A1 curves with type tau. This is a tropical type, combinatorial type tau and class beta, and which touch the toric boundary at one point with specified contact order, and the contact order is encoded in the data of a vector V in Rn. So this V encodes the contact data. So this is the canonical wall structure consisting of codimension Lansas with functions which I call wall crossing functions that are purely defined purely enumeratively. The example of such a structure, if you blow up P2 not at a toric point, but this time at this non-toric point, so P2 did admit a non-singular torus vibration over this momentum point of this triangle. If I blow up a non-toric point, now I have a singular vibration. There is going to be a singular torus, an nodal elliptic curve over this point, and the momentum polytope is no more the triangle, but you chop off this red triangle and identify this edge with this edge, and that will be the analog of your momentum polytope, which in 2D is studied extensively also in the work of Margaret Symington as almost toric-based diagrams. And in general, in higher dimensions, you always get some singular affine structures, by which, I mean, you can cover such manifolds with charts where the change of coordinate functions are in GLN Z, semi-direct product Cn. So this is an integral affine manifold with a singularity. You, on the fun side, also get an integral affine manifold with a singularity. So the fun, the analog of the fun for the blow-up of P2 at a single point is given by this picture where you a priori ignore the blue rays that I draw. It's just the fan of P2 together with this red region that is chopped off and the edges glued together. And you can understand this just by studying what happens if you blow up here to the self-intersection numbers of the boundary divisors. So this becomes 0, it was 1, it becomes 0. So how do you compute 0 self-intersection? You need this line to come to here to become this line and so on. So I do like to draw all the classes of the boundary after my blow up to remember the kinks of my PR function. And then, apologies, so I do want to also keep track of the A1 curves. So that's the additional data I need to define a wall structure. So I have two A1 curves. Exceptional curves are always A1 curves. They always touch a toric boundary at one point. So I encode the data of this by saying that I add an additional blue ray on top of the ray of the fan of this P2. And I add this additional wall crossing function given by 1 plus xt to the class of this curve. So if I would have a toric variety, I would just glue F1 pieces together in a natural way. But because I don't have a toric variety, there need to be some non-trivial gluings, and this function is going to tell me how I'm going to glue the F1 pieces adjacent to it, how my monomials change, and so on. But if I do this gluing only according to this function, I don't end up with an algebraic variety or anything nice. And to be able to do gluings and end up with an algebraic variety, the cool observation is that you need to add all of the A1 curves, all rays here, and all functions corresponding to all A1 curves. So I have another A1 curve whose class is L minus E, and glue by making use of the gluing defined by all these wall crossing functions, instructing me how my monomials will change across these walls. Okay, so just let's look at the mirror. If I blow up P2 at a single non-toric point, I have this whole structure. And now you can again just write your theta functions, pick a point. I like picking the point in the positive octant and impose my PR function to vanish there. The subtlety is when you have an integral defined structure, it's not so more easy to define the PR function. You actually don't have a PR function. Because around origin, there was no singularity. You were defining a PR function which was linear on every maximal cone. Now you have what is called a multi-valued PR function. So you have a PR function if you cover your integral defined manifold with singularities. With charts, on every chart you have a PR function, and they don't need to agree on their common intersection point. So it's multi-valued. So gluing the monoid rings defined by the upper graphs of the PR functions is a bit more subtle. And another subtlety is, as you see, when you want to draw down your broken lines, they bend because there are all these defined singularities. So you come from here, you bend to this direction. So your theta 1 0 is x, but your theta 1 bends, and it actually becomes x, y because of this defined singularity. And then there are all these walls when you write your theta minus 1 minus 1. You come from x inverse y inverse, so there's this one here. It just takes the contribution by, you have the option just to go straight and just take the contribution from the kink. Or another possibility that could happen is you multiply it with this and then take the contribution of the kink. So you multiply x inverse y inverse with this wall, and your theta minus 1 becomes this function. Then these are your 4 theta functions. You can write the mirror again like this. But it's, as you see, a little bit more complicated to write the mirror. And generally, it's much more complicated because there are not only A1 curves that are obtained by exceptional curves and the curves that go just straight across them. But in general, if you blow up, like if you blow up 2 points, you don't have only these things that go across, but things interact. So if you blow up 2 points in P2, if you take the strict transform of a line in P2 which passes those 2 points, you get another -1 curve which is like on the base, I illustrated like this, which is like sphere over this green thing. So generally things interact and you have more and more and more walls, and you need to keep track of those things as well. So it's solvable to take care of all A1 curves. And how do we take care of them? So I want to tell you the enumerative problem we are interested in solving. So we're interested in counting all A1 curves. So let me state the enumerative problem. So you fix beta, a in 2D, I will state it first, in a two-dimensional cone, and you fix a two-dimensional cone, and in the tropicalization of xt, and you fix a vector VAB, in this case I fixed, and you look at all A1 curves of class beta which intersect D with multiplicity AB. So fixing a vector in a two-dimensional cone, if this is AB, it means that if you just would look at this ray going through infinity in the AB direction, this would correspond to the tropicalization of a curve which intersects the divisor in 1, 0 direction with A and 0, 1 direction with B. And this would, because you impose, you want to intersect your boundary divisor at a single point. If both A and B were non-zero, they will just be corresponding to curves touching in the intersection of things. Those generally can happen. And the DP5 example that I draw, all non-zero A1 curves, all A1 curves happen to be if A or B, AB is among one of these rays. So all in this particular example, all curves really touch the interiors of the toric boundary. And a question people usually ask is, why in your enumerative problem do you also fix AB? Isn't it enough just to fix the beta? Because fixing beta in a toric variety amounts to fixing all contact orders. But by fixing AB, you actually fix something in additional, because you fix the maximal cone, and it amounts to also additionally fixing the strata, the toric strata, where you impose your contact orders. Like you can imagine, you can have a P1, another P1 touching at 2 points, and you will not be able to distinguish if you just fix beta, if your curve touches at one of them or the other. But by fixing the maximal cone, you specify some additional data if by fixing this V. And in higher dimensions, it's more difficult to state the enumerative problem in higher dimensions, but I just want to say that in higher dimensions, what changes from the two-dimensional situation is that you also have negative contact orders. So this picture I saw in the latest paper of Cross-Ebert, where they describe canonical wall structures and show that at any dimension canonical wall structures are consistent. Which is a difficult thing to show, but what happens, like there's an example they draw, they consider, just for trying to tell why you have negative contact orders, they consider DP7, like P2 blown up at 2 points, times P1, and then they blow up. So I tried to draw the momentum point-up image of DP7 times P1, and they then consider the blow up of a P1 and one of the P1 times P1 faces. If you blow up such thing, so the tropicalization I draw for this, because there's a 1 per meter family of such P1s you can choose here, I draw all these tropicalizations in red, and I draw just a slice of my fan picture. My corresponding fan will be just the fan of DP7, the blow up of P2 at 2 points, times the fan of P1. I'm just drawing the slice, which is interesting. So if I blow up, all these tropicalizations actually corresponding to the P1 will give me a codimension 1 cone, which is a wall in the language of all structures. And then if you look at the blue line here, its strict transform will be built by things like this. So again, there's a 1 per meter family, and these things just stop. So in the previous example, I had just AB. AB was recording to contact order, and it was always a positive multiple of the rays here. So if you have always a positive multiple, your contact order will always be positive. The only way you can get a negative contact order is if your tropicalization just goes and hits the boundary of something else, and this always happens in higher dimensions generically. So here, if you look at such a blue thing, it is obtained by this ray generated of this blue thing is this minus this actually. So it will have negative intersection here. So in higher dimensions, we have all this punctured log chromovitin invariants with negative intersections because we have this phenomenon where the tropicalizations go and hit the boundary of some other cones. And so I'd like to tell you a little bit about this. I want to tell how do we count such things which touch the boundary at one point and which might touch the boundary even in with negative intersections. So the problem to enumerate such things, if D would be a smooth divisor, it was proposed by Jun-Lee. So to construct a moduli space of A1 curves is subtle because when you touch the boundary at some point, you can imagine if you want to obtain a compact moduli space, things at some point might fall in the limit inside the divisor D, and then you might no more be able to keep track of the contact order. So what you need is create a bubble, and rather than looking at the curve that falls into D, look at the curve in the bubble. So he's creating all this what is called expansions by considering P1 bundles over D. Is everyone still hearing me? Can people occasionally show some sign that you're listening?
Yeah, we can hear you.
We're listening.
Okay, perfect, thank you. And what Abramovich, Shangro, Siebert do is they don't expand the target, they don't change the target, and they can do things in more generality when D is not smooth. I should say that I was recently trying to understand a lot of things in Jun-Lee's paper. I really admire this paper now, especially the degeneration formula of Jun-Lee. I noticed that a lot of people try to make generalizations of the degeneration formula, not paying attention to. I think it's an amazing paper. And if you look at what Abramovich, Shangro, Siebert does, this is also an amazing paper. So they replace the extensions. They don't expand. They replace the idea of extensions by rather using log geometry. So they do encode all the data that is needed for these extensions in some monoid, and they impose your domain curve to be log smooth over some basic monoid. So they can show that you can describe rather a monoid which encodes all the state of these bubbles and put some additional condition on your domain curve. And this condition is saying locally the morphism from your curve to this monoid ring should be, locally you should have a morphism of monoids. It's a technical condition, but they show that you can replace this extension business just by working over curves, by imposing some additional condition on their domains to be log smooth over some basic monoid. And then if you look at the moduli space of Abramovich, Shangro, Siebert, if you look at the moduli space of A1 curves with one punctured point, or could be positive or negative contact data, then this moduli space has dimension given by this, which equals dimension x minus 2. But then it follows from the construction of the basic monoid. They do also show that if you fix any combinatorial tropical type, then the strata corresponding to the type, such A1 curves, has dimension as much as the dual of the basic monoid. So even if in higher dimensions we have families of curves, like here we had a 1 parameter family of A1 curves and 1 parameter family here. So you can ask, how are we gonna ever count them if we have just families, no single curves? But log geometry allows you to count curves and families, so you need to count zero-dimensional strata in this moduli space. We actually look at maps where the basic monoid has dimension x minus 2, so you impose on your domain curve to be some condition that makes the count well-defined. And they do obtain animative invariance, even if the family, even if you have families, you count zero-dimensional strata in these moduli spaces. And this is the most technical slide in this talk. Apologies for that. I just want to mention that the way to define a virtual fundamental class in this moduli space is very subtle, because this is not what we call log smooth. But there's a very nice thing that you can do. There's some construction which is called an Artin fan. It's a log stack, and rather than looking at curves in X, you look at curves in this Artin stack. And this Artin stack is equidimensional. I mean, this Artin stack is nice. You can always define a virtual class if you look at the curves mapping to the Artin stack, and then you show that your moduli space has a nice two-term perfect abstraction theory to the moduli space of curves to the Artin stack, and then you just take some virtual pullback. Okay, so there is a very technical framework to define such invariance that's done by Abramovich and Gross-Ebert. And so the upshot is, if you want to write explicit equations to mirrors, you need to compute all possible A1 curves, which does require quite some technical framework. But we do solve this challenge. You don't need to really work as hard as one imagines with all these things that I taught in the last slide. In nice situations, there is some combinatorial way to obtain the counts of A1 curves, which we showed in our work with Mark. And then the second subtlety to write equations for mirrors arises because you need to write broken lines in the tropicalization of xt, which has all these affine singularities. And you need to keep track of how things bound with these affine singularities. In my paper that appeared on Archive this week, I showed that you also don't need to worry even about that. You can just forget about the singularities. You can push them away and use broken lines in Rn, and compute explicit equations in any dimension by pushing them away. And so if we want to compute A1 curves using Waltz, okay, so I want to start by telling this is the result of Mark and my paper. This is the result of my paper on Archive this week. I will start by telling how do you compute A1 curves combinatorially. So we do this by changing our setup. So there was this canonical wall structure that I told you about. It's used the enumerative information of A1 curves. I'm going to tell you about another wall structure. I will construct a wall structure in Rn without singularities, just in Rn, by taking a classical definition of a wall structure. And this definition of a wall structure appeared many years ago in works of Kontsevich, Zoibelman, and Gross-Ebert. I will call this the classical wall structure. I will use the classical wall structure to keep track of A1 curves in general locally via pairs. And that's what we do in our work with Mark. So I define a classical wall structure in Rn is a union of pairs consisting of codimensional subsets of Rn, together with wall-crossing functions, which are elements of a Lie group. And this Lie group is the group associated to the Lie algebra of what they call zero divergence vector fields on a family of tori. I wrote this definition, but I will explain concretely in a minute what my wall-crossing functions are. So you have a family of tori, spec Cm, if M is your lattice, and you take a family with with parameter T, and then you define a Lie algebra, and then you end up every wall with an element with the corresponding Lie group. And then there's a natural Lie bracket given by this. So your classical wall structure doesn't use any enumerative information. It only uses the information of Lie algebras and Lie groups. So your wall crossing functions are elements of the corresponding Lie group of the Lie algebra of vector fields on tori. And with Mark, we defined a combinatorial scattering diagram fitting into this classical definition of false structures of Kontsevich-Soibelman and Gross-Siebert. And we define it like this: if you have a local BR pair where X is obtained by a blow up of a toric variety along hypersurfaces, and if we define first an initial wall structure, which is given by a union of pairs rho I f rho I, where rho I are codimension one cells in Rn, and we define these initial walls just by looking at the tropicalizations of the hypersurfaces we blow up. And we don't only look at the tropicalizations, we look at the full deformation space of the tropicalizations. As an example, if you take P2, if you blow up two non-toric points, by blowing up a non-toric point, the tropicalization of a point is a point. But I want to take its full deformation space, which means I can move the point as long as I stay in the same cell of the toric fan of P2. So this is the deformation space, it's just a ray. And why do I take the deformation space? It's all about this basic monoid business. There's a purely combinatorial way to define the basic monoid encoding. So there was all this picture, this technical stuff, encoding if you look at, for instance, the log Gromov-Witten paper of Gross-Siebert, it's explained, there's a description of how to encode all the bubbling stuff into a basic monoid. You need as many copies of natural numbers as your node, and you need some more copies of natural numbers depending on how many components your domain curve has. But that definition can be turned into a purely tropical definition. If you tropicalize your curve, your basic monoids can be described just as it will have rank as the deformation space of the tropicalization of your curve. So it does really, if you spend some time, in my case, which was more time than I'd like to admit, to understand this, what's going on with log geometry, it makes sense to take the deformation spaces of tropicalizations to define your initial walls. And then you attach wall crossing functions of the form 1 plus tiz to mi to the corresponding walls. And this is, you declare this to be your initial wall structure defined purely combinatorially just by the initial data of what you blow up into your toric variety. As an example, if you blow up lines in P3, if you take two lines in the toric boundary, different toric boundary components, I drew the fan of P3. This is the, the tropicalization of a line given by this. So you take the deformation space, you obtain 6 walls. On the trio of them, I attach 1 plus T1x. On the trio, I attach 1 plus T2y. And when I first understood that it's the right thing to take deformation spaces of lines, I first fiddled so much with this example and computed some superpotential using broken lines. And when it gave the right thing, I went to Mark and said, this is such a cool thing, it just works. You take just the deformation classes to define your initial walls, and I was so happy. And then Mark pulled up a few pages written paper where he defined them exactly like this, saying he had that idea some years ago, but it was not written. So we wrote how to make use of this initial thing and turned it into a paper. And there in those notes, these things, very, very cool things, were called widgets. So we call them widgets. So these are 2 widgets. And when you have these widgets, when you have your initial walls, when you have a scattering diagram, what you can do is you can cross walls. So if you have a wall with normal vector and you take a normal vector depending on, you can define a normal vector depending on, you take always around joints where your walls intersect, you go around loops around joints, and you can choose a normal vector accordingly. You cross walls by mapping your monomial to the wall crossing function times you have the power paired with the normal vector z to mi. And to declare, apologies, I wrote switch between wall structure and scattering diagram. You declare a scattering diagram or a wall structure to be consistent If around any joint where your walls intersect, the composition of all wall crossing transformations give you identity. Unfortunately, as you can imagine, the initial wall structures, if you just have these two rays or these walls, they are never consistent. But there is a nice algorithm to complete the wall structure to a consistent one, purely algebraic algorithm. So it says how to systematically insert walls to complete the initial scattering diagram to a consistent one, to a consistent wall structure. So this is a purely algebraic algorithm, and we wrote a code with Tom codes. Essentially, he wrote it to run this algorithm using Magma computer algebra, which I'm very grateful that he did that. Otherwise, I wouldn't be able to compute the explicit equations that I will tell you in a moment. So, for instance, if you if you run this algorithm for the two widgets here, you see that you need to insert all these walls to obtain a consistent scattering diagram. Actually, I think that was not easy because the algorithm tells you at each step. So if you take set around this joint, the monomial Z, and see how much it diverges from coming back to Z. Say it diverges, but so Z, if you carry around Z with apply all these things, so it diverges by a monomial, you just correct it by adding a wall with a function 1 plus that monomial or 1 minus that monomial. So the algorithm tells you at each step what to add a wall to decrease the divergence. But here you see there are things of the form 1 plus something plus something. This means that in this example, we actually had infinitely many walls, and the algorithm never stopped. But we observed that we guessed, and it turned to be correct. We proved that those infinitely many walls could be replaced by finitely many walls with these attached wall crossing functions. All right. So what the main result of our paper with Spark is, and what is shown already in dimension 2 by Gross-Ponder-Panda and Siebert, is saying this. If you have a local Hülya pair with a toric model of dimension n, and if you build this initial wall structure that I described combinatorially using the tropical data of things you blow up, and if you run the algorithm tells you, you started all this algebraic algorithm, but it tells you enumerative information. It tells you that the walls you add to complete it to a consistent scattering diagram satisfy this property. The log f out is a series capturing this numbers of A1 curves. So this algorithm is run by just looking at the structure of this Lie group. You do some commutator computations, but at the end of the day, you end up with getting enumerative information out of an algebraic structure. And the idea of the proof is as follows. So if you want, what you do is you have your xt, you construct a degeneration of xt to the normal cone, which means that you degenerate xt into a toric variety. The toric, like if you, for instance, consider P2 blown up at a non-toric point, you can degenerate it into P2 union P1 bundles over the toric boundary, in this case, which is just a Hirsebruch surface. And then the degeneration formula says that you can count all A1 curves in xt, you can obtain them in terms of counts of curves in the toric, relative curves in the toric piece, plus curves here, which can be computed easily using some multiple color formulas. I'm using a big analog of the degeneration formula, which is actually stated wrongly also in some papers that I saw, because it's not true that if you compute invariance of the central fiber, many people state the degeneration formula saying you degenerate, if you compute on your central fiber into two pieces, your relative invariance, they give invariance, you can obtain in the general fiber your Gromov-Witten invariance. But there's a subtlety, you actually obtain sums of Gromov-Witten invariants, because some map from the general fiber to the total space is not on some class level, doesn't need to be injective and so on. And yeah, so, but here everything works well. So in this paper with Mark, we show that you can actually use the idea coming from the generation formula to reduce your enumerative problem to an enumerative problem into a toric piece and into another piece that you can solve. And the enumerative problem in the toric piece has the advantage that you can solve it using tropical geometry. So that's why how the canonical scattering diagram and the combinatorial scattering diagram are actually very closely related. So if you, as a consequence, you can combinatorially construct actually the canonical wall structure. That's what we showed. So if you look at the tropicalization of the total space, and if you look at the central fiber of this total space, which is a degeneration to the normal cone, it is a map to r greater or equal 0. And if you look at its height 1 slice, then it looks like this in the example of P2 blown up non-torically. What you obtain at the end of today, you move away the singularity in this canonical scattering diagram. And we analyzed the height 1 slice. Around the origin, it's turned to be just the combinatorially constructed scattering diagram, by which I mean there is a Theta function around the origin of the slice, which is just taking the combinatorially constructed scattering diagram associated to xt to here. And if you just ignore what happens around the origin and look at the finite, infinite rays, they just correspond to walls of your canonical scattering diagram. And so we proved that you can just study the combinatorially constructed scattering diagram, and by studying that, you can understand your canonical scattering diagram. Proving this required analyzing that your canonical wall structure has some very nice property that nothing crazy is happening in infinity to destroy this nice thing around the origin. The structure is called radiance. It says roughly that if you have a point on a wall, the whole ray containing that point needs to be inside the wall. And this required proving, this was the most difficult part. It required a lot of new ideas. And there was also a part which required a lot of technical craftsmanship, showing that if you analyze around the origin part, you can understand the canonical wall structure, which required doing all this monodromy analysis around this integrally affine part. And for that was the cumbersome part. So I think you made a fair deal with Mark to share this part requiring experience of him versus part requiring some technical craftsmanship. And so I did all these monodromy computations, which were very useful to understand how to write broken lines in the paper that appeared on arXiv today. I noticed that you don't really need to write broken lines in the canonical wall structure, because the monodromy is so nicely computed that you can just forget about it and write broken lines around origin where you don't have any singularity. So I defined the heart of the canonical structure associated to a local BR pair as follows. So you have this canonical scattering diagram associated to the degeneration at its side 1 piece. You have all these multi-valued PR functions with these kinks. Around the origin, they restrict to a single PR function. So there are classes which belong to the total class, the fiber classes, which are not parts of X. I declared them, just put them to be 0. And I showed you still would get a consistent wall structure if you put all these classes to be 0. And then this wall structure, the advantage of this is it's constructed purely combinatorially from the wall structure described using the classical setup of Lie algebras and stuff. So there is some work to do to describe how to pass from TI variables to Kerr class variables, which is nicely explained in our paper with Mark. And the way it goes is if you have an initial wall, which is a wall corresponding to exceptional things you blow up, if you equate all fiber classes to be 0, your initial walls, TIs, will just turn to Z to minus E's. But to describe what happens to the outgoing walls, you need to do some analysis. So you see if your wall crossing function is of the form 1 plus T1x, if you blow up more points, it will be 1 plus T. If you blow up a higher multiplicity, it will be 1 plus T1x to some power. And then these functions, however, are always power series of this form. And then from the state of these aij's, you can first define a toric class using the PL function, and then by taking the pull back to the xt. So there's a way to pass from Ti to Kerr class variables that we described. Okay, so the upshot is, just to wrap up, the main theorem is for a general point around the origin. If you take a general point, and if you define theta functions by broken lines there, without worrying about the affine singularity, just by forgetting about all the affine singularities that are outside, then you get the ring of theta functions. Your ring of theta functions was defined by taking a point outside where these walls correspond to walls of the canonical wall structure and things band and so on. But I claim that you can just forget everything that's happening outside and take a point here and write theta functions defined by broken lines here. And you will get an isomorphic ring to the ring of theta functions. And this uses observing that every theta function you write here is obtained by a nice parallel transport map. You actually just apply a parallel transport map to the theta functions here. So that parallel transport map induces an isomorphism between the ring you obtain from here and the ring of theta functions. Can I just have 3 minutes? Do I have 3 minutes to go through examples still?
Yeah, it's not quite 1 o'clock, so you've got 3 minutes left.
Okay, thank you. Maybe I might go just a couple of minutes, like 5 minutes, maybe. Sorry. So maybe I would like to go through I feel like I told a lot of things, but maybe I'd like to go through this 2 examples I wrote slightly bit slower. So what happens if you want to write a mirror of P3? And if you blow up P3, if you blow up a line non-torically and one toric boundary component P2 of P3, then you have an initial widget formed by the light blue thing, which is obtained by tropicalizing your line and moving it. And to complete it to a consistent scattering diagram, so the attached functions to this thing combinatorially were all 1 plus T1x. And if I don't blow up a line, but the degree D hypersurface, like a conic D would be 2, then I put 1 plus T1x to the D. And because it's an initial wall, I treat my formal variable appearing in the combinatorial construction just by T to the minus the exceptional class. And to complete it to a consistent scattering diagram, I just continue with these widgets. In the combinatorial construction, I would have 1 plus T1x to D again, but then I run the recipe to tell you what the correct Kerr class variable is to put here. There's some recipe described in our paper with Mark. And then this is a scattering diagram with no singularities whatsoever. So I fix a point and I just write my broken lines defining theta functions at this point to understand what the mirror is. So I fix a point in the positive octant from X, Y, and Z direction. My broken lines never cross anything. So theta E1 is X, theta E2 is Y, theta E3 is Z. And theta E4, which is the -1 minus E1, minus E2, minus E3 direction only crosses this wall with this attached wall crossing function, and it turns into 1 on xyz times this. So the mirror in this case is generated by these 4 theta functions because I have 4 rays again satisfying this equation. And if you blow up not only one hypersurface, but more hypersurfaces, if you take another hypersurface on this side, then things will interact and there will be a lot of wall crossing, which is difficult to keep track of. But I observed that all this wall crossing doesn't really affect your ability to write the equation of the mirror because easily, only if you observe that if you do wall crossing, if you blow up a hypersurface of degree d1 on this side and of degree d2 on the other side, you need to add infinitely many walls, but those infinitely many walls turn out to be added always on the xy plane, and they always accumulate on some part of the xy plane. So here on one part corresponding to the positive octant, so I just drew the 2D slice of the xy plane, so of the 3-dimensional R3. So this is the xy plane. So you have some nice E1, E2 chamber where you know your attached wall crossing function. And you again, if you pick up a theta function, if you want to write your theta functions, that will be the only wall you're crossing. So I wrote the mirrors in these cases, obtaining explicit equations for mirrors. If you blow up disjoint unions of hypersurfaces along boundary divisors of P3 by observing that there's some nice accumulation of the walls that you need to add in the thing. The final slide, how does all this story relate to Fano-mirror symmetry? If you define your tropical superpotential by summing up all your theta functions, then this tropical superpotential, if your x is Fano, agrees with the superpotential that is computed by the Fano search team, Korti, Skakin, and Kasprzak. And not all local BR pairs where you blow up disjoint unions of hypersurfaces are toric, but I verified this in all cases, such situations are toric. Like if you blow up a line here and a line here, or if you blow up a line here and a conic here, then we observed, actually, this was one of the first observations we had while we wrote this project. The tropical superpotential agrees with the Korti, Skakin, Kasprzak superpotential. I think it's a nice point to stop, probably. Apologies, I'm a couple minutes over time. Thank you.
I will stop the recording.